Welcome to Minuteman Technology's Power Basics 101 training. We're glad you decided to join us, and we hope you learned something today. The topics we'll cover in today's presentation include explaining a little bit more about power between voltage, amperage, and volt amps, also known as VA. We'll discuss what exactly is a power factor. We'll discuss the current types of power, including alternating current, AC, direct current, DC, and what it looks like in comparing AC to DC power. We'll also discuss batteries and their runtimes. We'll explain frequency. We'll dive into voltage variances, and then we'll cover the NEMA plug types and receptacles.
Power explained. What is voltage? This foundational concept in electricity is key whether you're troubleshooting a circuit or just curious how your phone charges. Voltage is defined as the variance of electric potential energy transported between 2 points. It's often described as the electrical pressure that pushes electric charges through a conductor like a wire. It's what makes electric current flow. The technical term for voltage is electromotive force, EMF, which simply means how much energy the electrons consume. Think of voltage like water pressure in a hose. The higher the pressure, the more forcefully the water flows. Similarly, higher voltage pushes more electrical current through a circuit. When trying to measure voltage, the device used is called a voltmeter or a multimeter, and the units are measured in volts. Some common voltage levels include a AA battery at 1.5 volts, a car battery at 12 volts, and household outlets in the US at 120 volts. Let's use a simple battery to explain. Imagine a AA battery. It has a positive and a negative terminal. Inside, there's a chemical reaction creating an imbalance of electric charge. The voltage is the difference in electric potential between the two terminals. This voltage is what pushes electrons from the negative side through a circuit and back to the positive side, powering devices like flashlights or remote controls. In a basic electrical circuit, you'll usually see a power source, like a battery, a load, like a light bulb, and conductive wires. When the circuit is closed or connected, voltage from the battery drives the current through the wires and into the bulb, lighting it up. No voltage, no push, and no current flows. An important safety note, higher voltage means more risk. While 1.5 volts, like a AA battery, is harmless, touching a 120 volt or 230 volt outlet can be dangerous or even fatal. Always follow proper safety procedures when working with electricity. Power explained. What is amperage? Adding to our foundational concept of electricity, amperage or amps is defined as the measure of electric charge flowing through a circuit per second. So if voltage is the push, amperage is the flow. Voltage is what gets the electricity moving, whereas amperage is the actual movement of electric charge through a conductor. Amperage is also called current. If you're going to measure amperage, the units would be measured in amperes or amps for short and is represented in equations by a capital A. The tool you'd use to measure the amps is called an ammeter, or more commonly, a multimeter set to current mode. Some common reference points: a phone charger is 1 to 2 amps, a toaster is 10 to 12 amps, an electric vehicle charger is 30 to 50 plus amps. Continuing with our earlier analogy, if voltage is the water pressure, amperage is the amount of water flowing through the hose or the flow rate. In an electrical wire, the water is actually electrons, and amperage tells us how many of them pass a point in the wire every second. Remember, in a basic electrical circuit, you have 3 parts: a power source, like a battery, a load, like a light bulb, and conductive wires connecting them. When the circuit is complete, voltage pushes electrons through the wires, and amperage is the rate at which those electrons move. More amps equals more electricity flowing equals more power being used by the device. Voltage and amperage do not act parallel to or mirror each other. You can have high voltage and low amps, like a stun gun, or low voltage and high amps, like a car starter motor. The real danger often comes from high amperage. As little as 10 amps through the human body can be fatal under the right conditions. Understanding amps is important for many reasons. It tells you how much power a device draws, it helps you size wires and breakers correctly, and it prevents overheating and electrical fires. Too many amps through a small wire can be a huge fire risk. Power explained. What is a volt amp? The unit of electrical power you may not hear every day, the volt amp or VA, is the unit used for the apparent power or potential power in an electrical circuit. If you work with uninterruptible power supplies, UPS, servers, or commercial power systems, VA readings are everywhere. So, what do they really mean? Let's break it down. In electrical systems, power is how much energy is being used or transferred over time. There are two main types of power. Real power, measured in watts, represented by W, the actual power your device consumes. We'll talk more about this in terms of a power factor next. And apparent power, measured in volt amps or VA, the total power flowing through the circuit, and that's where volt amps come in. A volt amp is a unit of apparent power in an electrical circuit, and it's calculated by multiplying voltage by current, and then you get volt amps. So why do we care about volt amps? Because electrical infrastructure like UPS units, generators, or transformers must be sized based on VA and not just watts. If you size a UPS for only the watt rating and ignore VA, you risk overloading it, even if the device seems underused. Let's look at some examples. A server might use 600 watts but draw 750 VA. A UPS rated at 1500 VA with a power factor of 0.9 can safely handle 1,350 watts. Always check both ratings when sizing or selecting equipment. The easiest way to do the math is to let sizemyups.com do it for you. It's Minuteman Power's free online tool. Work smarter, not harder. In case you forgot to take notes the first time, go to sizemyups.com. Power factor is a measure of how effectively electrical power is being used. It is defined as the ratio between real power and apparent power. To solve for power factor, divide the real power by the apparent power. The real power is the actual power that does useful work, like turning a motor, and apparent power is the total power supplied, which includes both the useful power and wasted energy. Power factor is a number between 0 and 1, and it's expressed as a percentage. There are three types of power in AC circuits. Real power does the actual work. Reactive power does not do the work but is necessary for maintaining voltage levels used by motors or transformers. And apparent power, the combination of real and reactive power. Think of apparent power like a beer. The whole mug is the apparent power, the whole beer. The foam on top is reactive power, and the beer is the real power, i.e., how much beer or power you really have. What's an ideal versus a poor power factor? An ideal power factor is 1 or 100%, meaning all the power is being used effectively. A poor power factor, i.e., 0.7 or 70%, means you're paying for power you're not fully using. Why does power factor matter? Well, 4 simple reasons. Number 1, cost savings. Using devices with a low power factor means you're paying for energy you're not getting the benefit of using. Number 2, energy efficiency. A better power factor is more efficient power use. Number 3, equipment longevity. A poor power factor can stress generators, transformers, and cables. Number 4, reduced losses. High current caused by poor power factor equals more heat and energy loss. Power current types. Alternating current, AC, is a type of electrical current where the direction of the flow of electrons periodically reverses and changes direction in a wave-like pattern, usually many times per second. AC is usually represented as a sine wave. How is AC generated? AC is generated by alternators at power plants. A rotating coil inside a magnetic field induces an alternating voltage. This rotation creates a waveform where polarity switches back and forth. Why do we use AC? Well, it has an efficient transmission. AC can be transformed to high voltages using transformers for long-distance travel, reducing energy loss. Another reason is it's flexible with the voltage control. AC voltage can be stepped up or stepped down easily. And third, it's a standardized form of power. Most home and industrial devices are built for alternating currents. Some examples of alternating currents in real life include power outlets in homes, industrial machines and motors, household appliances, and street lighting. Note, many devices internally convert AC to DC like laptops and TVs. There are two kinds of AC power, including single-phase and three-phase. Single-phase AC is common in homes and uses two wires, a hot and a neutral. Three-phase AC is used in industries and is more efficient for heavier loads. Three-phase delivers power more smoothly and involves three alternating waveforms offset by 120 degrees. Power current types. Direct current, DC, is a type of electrical current where electrons flow in one consistent direction from the negative terminal to the positive terminal of a power source. Unlike AC, the voltage and current in DC do not alternate, they remain steady over time. Some key characteristics of DC is the unidirectional flow, where the current always flows the same way, the constant voltage with no reversal of polarity, the fact that it's easier to store and is the standard for batteries and energy storage, and it's typically lower voltage used in electronics and small devices. Some applications of DC power include your electronics, such as your computers, your mobile phones, televisions, vehicles, such as e-bikes and electric motors, solar energy systems, telecommunications, the backup power and equipment for those, as well as LED lighting. Nearly every modern electronic device uses DC internally, even if powered by AC from a wall outlet. DC is ideal when you need steady, reliable, and low voltage power, especially for electronic circuits. Power current types, AC versus DC. Both AC and DC have their own unique advantages. AC advantages is it's easy to transmit over long distances, voltage can be increased or decreased with transformers, and it's the standard for power grids. DC advantages, it's stable and reliable for electronics, it's easier to store, i.e. batteries, and it's essential for digital devices and renewable energy systems. For use case scenarios, you're going to want to use AC when you need to power large systems over long distances, or you're working with building wiring or appliances. You're going to want to use DC when you're powering electronics or circuits, you need portable or battery-based power, or you're working with renewable energy sources. Batteries and runtimes. Whether you're in customer support, sales, or service, understanding how batteries work and how long they last, i.e. the runtime, is essential to helping our customers choose the right product and use it effectively. A battery, as everyone knows, is a device that stores energy and converts it into electrical power. Think of it as a fuel tank for electronics. Battery terms you'll need to know include voltage, capacity, and watt hours. To estimate runtime, watt hours give the most complete picture. It's like knowing both the size of a gas tank and how fast the fuel is used. Things that are going to affect your battery runtime depend on three major factors: your battery capacity, your power consumption of the device, and environmental conditions. For your battery capacity, more amp hours equals a longer runtime. For your power consumption of the device, high-powered tools drain batteries faster. And for your environmental conditions, cold weather reduces efficiency. For estimating runtime, let's say you have a 20-volt battery with a 5 amp hour capacity. First, calculate watt hours. 20 volts by 5 amp hours equals 100 watt hours. Now, suppose the tool uses 50 watts of power per hour. Estimated runtime is 100 watt hours divided by 50 watts equals 2 hours. So in ideal conditions, that tool would run for about 2 hours. Here are a few tips to help maximize runtime. You're going to want to fully charge batteries before their use. You're going to want to store batteries at room temperature. You're going to want to use the right battery size for the job. And you're not going to want to over discharge. You're going to want to recharge it before it hits 0%. And of course, keep your batteries clean and dry. Batteries and backup power are critical to performance. When you understand how voltage, capacity, and power consumption work together, you can help customers choose better and use smarter. Bigger capacity and lower power draw equals longer runtime. Remember, the easiest way to do the math is to let sizemyups.com do it for you. It's Minuteman Power's free online tool. Work smarter, not harder, with sizemyups.com. What is frequency? It's a simple concept at its core, but it's critical in everything from electrical power to wireless signals, audio, and even your microwave. Frequency is how often something happens, specifically how many times a wave repeats in 1 second. It's measured in hertz, represented by a capital H lowercase z. So if 1 hertz equals 1 cycle per second, which means if something happens 60 times per second, that's 60 hertz. Here's how frequency shows up in your daily life. The electricity in your home, for example. In the US, the standard is 60 hertz AC power. In many other countries, it's 50 hertz. That's how often the electrical current changes direction each second. Another example of frequency in your life is sound in music. A low bass note might vibrate at 50 hertz. A high-pitched whistle could be 5,000 hertz or more. Our ears typically hear between 20 hertz and 20,000 hertz. Another example of frequency is our wireless communication. Wi-Fi, 2.4 gigahertz and 5 gigahertz. That's billions of cycles per second. Radio, AM is in kilohertz and FM is in megahertz. But why does frequency matter? Understanding frequency is important because it affects how systems behave. Electrical equipment compatibility. Devices must match the power frequency. Signal clarity and range. In communications, different frequencies have different ranges and data capacities. And the component design. Speakers, antennas, and circuits all work best at certain frequencies. There's a difference between power frequency and signal frequency. Power frequency, 50 to 60 hertz, is found in alternating current power systems. It impacts how motors run, lights flicker, and how transformers work. Signal frequency, kilohertz to gigahertz, is found in audio, radio, cell phones, Bluetooth, etc. It's a higher frequency, which equals a shorter wavelength, and is often faster at communication but shorter in range. We introduced voltage earlier. Now let's talk about voltage variances. Remember, voltage is like water pressure in a pipe. More pressure is more force. High voltage is a stronger push, whereas low voltage is a more gentle push. Different systems use different voltages for different reasons. Let's look at some common categories. Your low voltage will be under 50 volts, and some examples include batteries, USB ports, LED lighting. Generally safe to touch, though still use care. Next is your standard household voltage. That means 120 volts in US and Canada and 230 volts in Europe, Asia, and most of the rest of the world. Your high voltage is going to be over 480 volts. This is going to be used in industrial motors, transmission lines, substations. It's extremely hazardous and requires special training and gear. But why does voltage variance matter? Well, it matters for your device compatibility. A 120 volt appliance will fry if it's plugged into a 230 volt without a converter. Also, your power needs. Higher voltage systems can deliver more power with less current. An example would be industrial machines use 480 volts to reduce wire size and heat. And third, safety. Higher voltage equals higher risk. Always know the voltage before working on a system. How you identify voltage includes labels and nameplates on tools or equipment, color-coded wires, multimeter or voltage tester, and user manuals or product specs. Never assume, always verify. NEMA plugs and receptacles. Have you ever looked at an electrical outlet or plug and wondered what those strange numbers mean, like NEMA 5-15R or L14-30P? Let's ask NEMA. NEMA stands for National Electric Manufacturers Association. It's the body that sets standards for electrical equipment, including plugs and receptacles used throughout North America. Their goal is to ensure compatibility, safety, and consistency across manufacturers and industries, which is why you may have noticed the numbers on an outlet or a plug, to make sure the right plug fits the right power source safely and reliably. The NEMA numbering system includes NEMA, then a number that represents the configuration, a dash, the number that represents the amperage, and then a letter that represents the type. Let's break down an example. If you see NEMA 5-15R, the 5 is the voltage and configuration type, the 15 means the device is rated for 15 amps, and the R stands for receptacle, or there will be a P if it's a plug. So a NEMA 5-15R is a standard 120 volt outlet you'd see in most US homes. There are two types. You have straight blade versus locking. Straight blade plugs go in and pull out like regular cords. Locking types twist to lock in place so they don't disconnect by accident. Think of industrial or commercial use scenarios. Plug and receptacle compatibility. It's important to note NEMA plugs and receptacles must match exactly to connect safely. A 5-20P plug won't fit a 5-15R outlet, and that's by design. We want to prevent overloads or unsafe wiring. Never modify a plug to fit a different receptacle, and always check voltage, amperage, and configuration.